In this episode of the podcast, we will talk about Kubernetes services. The main use of these services is connecting users to pods. To access the application, a user or a client needs to connect to the pods. As pods are ephemeral in nature, resources like IP address cannot be static. Pods could be terminated abruptly or be rescheduled based on existing requirements. Let's take, for example, a scenario which a user or a client is connected to a pod using its IP address. A scenario where a user is connected to a pod via its IP address. Unexpectedly, the pod to which the user is connected is terminated and new pod is created by the controller. The new pod will have a new IP address which will not be known automatically to the user of the earlier pod. The second scenario is a new pod is created after the old pod is terminated unexpectedly. To overcome this situation, Kubernetes provides a higher level abstraction called service, which logically groups pods and defines a policy to accept them. This grouping is achieved via labels and selectors. A Kubernetes service is an abstraction which defines a logical set of pods running somewhere in your cluster that all provide the same functionality. When created, each service is assigned with a unique IP address known as the ClusterIP. This address is tied to the lifespan of the service and will not change while the service is alive. Pods can be configured to talk to the service and know that communication to the service will be automatically load balanced out to some pod that is a member of the service. As I have mentioned before, a service is backed by a group of pods. These pods are exposed through endpoints. The service selector will be evaluated continuously and the result will be posted to an endpoints object. When a pod dies, it's automatically removed from the endpoints and new pods matching the service's selector will automatically get added to the endpoints. Kubernetes supports two primary modes of finding a service: environment variables and DNS. The former works out of the box, while the latter requires the core DNS cluster add-on. Before exposing the service to the internet, you want to make sure the communication channel is secure. For this, you will need self-signed certificates for HTTPS, unless you already have an identity certificate, a server configured to use the certificates, and a secret that makes the certificates accessible to the pods. Now let's talk about something called EndpointSlices. EndpointSlices provide a simple way to track network endpoints within a Kubernetes cluster. They offer a more scalable and extensible alternative to endpoints. The Endpoints API provides a simple and straightforward way of tracking network endpoints in Kubernetes. Unfortunately, as the clusters and services have grown to send more traffic to the backend pods, limitations of that original API became more visible. Most notably, those included challenges with scaling to larger number of network endpoints. Since all network endpoints for a service were stored in a single endpoint resource, those resources could get quite large. That affected the performance of the Kubernetes components, most notably the master control plane, and resulted in significant amount of network traffic and processing when endpoints changed. EndpointSlices help us mitigate those issues as well as provide an extensible platform for additional features such as topological routing. By default, the control plane creates and manages the endpoint slices to have no more than 100 endpoints each. You can configure this with the max endpoints per slice flag, and it can be set up to a maximum of 1000. Endpoint slices can act as the source of truth for kubeproxy when it comes to how to route internal traffic. When enabled, they should provide a performance improvement for services with large number of endpoints. Now we need to know about what kubeproxy does when it comes to service. Before that, let's have a brief recap about kubeproxy. Kubeproxy is the network agent which runs on each node and is responsible for dynamic updates and maintenance of all networking rules on the node. So all worker nodes run a daemon called kubeproxy, which watches the API server on the master node for addition and removal of services and endpoints. For each new service on each node, kubeproxy configures IP table roles to capture the traffic for its ClusterIP and forward it to one of the service endpoints. Therefore, any node can receive the external traffic and then route it internally in the cluster based on the IP rules. When the service is removed, kubeproxy removes the corresponding IP table rules on all the nodes as well. As services are the primary mode of communication in Kubernetes, we need a way to discover them at runtime. Kubernetes supports two methods for discovering services. The first one is environment variables and the second one is DNS. As soon as a pod starts on any worker node, the kubelet daemon running on that node adds a set of environment variables in the pod for all active services. Kubernetes has an add-on for DNS, which creates a DNS record for each service. Services within the same namespace find other services just by their name. If we add a service, all pods in the same namespace look up to the service just by its name. Pods from other namespaces look up the same service by adding the respective namespace as a suffix. This is the most common and highly recommended solution. Now that we've known about services, let's talk about the different types of services. The first one is ClusterIP. ClusterIP is the default service type. A service receives a virtual IP address known as its ClusterIP. This virtual IP address is used for communicating with the service and is accessible only within the cluster. The second one is NodePort. With the NodePort service type, in addition to a ClusterIP, a high port which is dynamically picked from the default range of 30,000 to 32,767 is mapped to the respective service from all the worker nodes. For example, if the mapped node port is 32233, if we need to connect to any worker node on port 32233, the node would redirect all the traffic to the assigned cluster IP. If we prefer a specific high port number instead, then we can assign that high number port to the node port from the default range. The NodePort service type is useful when we want to make our services accessible from the external world. The end user connects to any worker node on the specified high port, which proxies the request internally to the cluster IP of the service. Then the request is forwarded to the applications running inside the cluster. To access multiple applications from the external world, administrators can configure a reverse proxy, an ingress, and define rules that target services within the cluster. The third kind of service we'll be talking about is the load balancer. With the load balancer service type, NodePort and ClusterIP are automatically created, and the external load balancer will route to them. The service is exposed at a static port on each worker node. The service is exposed externally using the underlying cloud provider's load balancer features. The load balancer service type will only work if the underlying infrastructure supports the automatic creation of load balancers and have the respective support in Kubernetes. If no such feature is configured, the load balancer IP field is not populated and the service will work the same way as NodePort type service. Then we'll talk about external IP. A service can be mapped to an external IP address if it can route to one or more of the worker nodes. Traffic that is ingressed into the cluster with the external IP on the service port gets routed to one of the service endpoints. This type of service requires an external cloud provider such as Google Cloud Platform or AWS. We should note that external IPs are not managed by Kubernetes. The cluster administrator has to configure the routing which maps the external IP address to one of the nodes. And lastly, let's discuss external name. External name is a special service type that has no selectors and does not define any endpoints. When accessed within the cluster, it returns a CNAME record of an externally configured service. The primary use case of external name is to make externally configured services like the database available to applications inside the cluster. If the externally defined service resides within the same namespace, using just the name would make it available to other applications and services within the same namespace. Okay, now that we have discussed different types of services, there's also something called an ingress. Ingress is also used to communicate with the application inside the cluster. But that's a little more lengthy and elaborate, so I'll be making a separate episode just on ingress.
If you like this episode, please consider following us wherever you hear your podcasts.